students, and welcome to this ninth lecture of the heat transfer course EEAQ 3235. And in today's lecture, we're going to have a look at convective heat transfer. Now, as you have noted, in the past 8 lectures, we've been focusing much more on conduction, heat transfer, and the only time that we've had a mention of convection is when we've applied it as a boundary condition, like in fins and its surroundings and their surroundings, semi-infinite solids and their surroundings, layered walls and their surroundings, etc. So today we're going to have a look at convection when it is the prevalent mode of a transfer. And as you can remember, we say that the rate of heat transfer by convection, its rate equation is given by the Newton's law of cooling, where Q is equals to the convective heat transfer coefficient H times the surface area A times the temperature difference between a hot surface and the flowing fluid. So Ts minus T infinity. So Q is the rate of heat flow inwards. Okay. Ts is the surface temperature, and T finite is as the fluid temperature at the free stream. The units of convective heat transfer are or is watt per meter squared Kelvin. Now, let us see what the mechanism of a convective heat transfer is. Now, and we've seen that in conduction, heat transfer is by interaction of atoms, molecules, etc. By movement of free electrons, vibration of lattice structure, etc. And there is no bulk motion of the material or the medium that is causing or through which heat is being transferred. Now, in convection, there must be a bulk motion of the material that is enabling our heat transfer, or through which we are transferring our heat. So, in convective heat transfer, we'll look at for illustration purposes, at a simple case whereby we have a surface, and on top of that surface flows a fluid. So we may be having a fluid that is flowing like that. Okay, so the flow is like that. Now, we'll visualize the fluid as if it was made of layers as shown on the diagram there. And we'll assume no slip. That is, there is no slip between the layer that is adjacent to the surface. To simplify things. So that means that the layer that is adjacent to the surface takes up the velocity of that solid surface. So if the solid is not moving at all, that layer adjacent to it will be having a velocity that is equals to 0. Now, bearing that in mind, let us have a look at the way the velocity and the temperature varies with the distance from the solid surface. So we have in this diagram our solid surface there. Now, we've said that the layer that is adjacent to the solid surface takes up the velocity of that surface. So supposing it is that the surface is stationary, so the velocity there of the fluid will be 0. And it increases parabolically as shown by that curve, okay, from 0 until it reaches the maximum velocity, which is the velocity at the upstream, right? And the temperature varies in almost a similar curve, but in the opposite direction, as shown from T, that is the temperature of the surface, to the temperature of the fluid at the upstream. Now, there is a small portion right there, and across this small portion the heat transfer is purely by conduction, and this small section here is called the boundary layer. And the boundary layer has a thickness that is denoted by a delta. That is, the boundary layer thickness is denoted by delta. And we've seen that across that small thickness the heat transfer is purely by conduction. Now, so what is the thickness of that boundary layer? The definition is, or the condition is, that this boundary layer, the velocity varies from, let's say, 0 to about 0.99, the upstream velocity. All right, so it varies from 0 to 0.99 of the upstream velocity. So that is our boundary layer, and these limits will give you the thickness of the boundary layer that we have said is denoted by delta. And we know that from the Fourier's law, Q is equals to minus Ka dt by, this time the variation is in the y direction, so d by dy, when dt by dy is measured at y is equals to 0. And we've seen that the Newton's law of cooling is Q is equals to HA Ts minus T finite. And from the law of conservation of energy, heat energy that is flowing from the surface in through the boundary layer into the rest of the fluid will be the same fluid that will flow out from the upstream of the fluid, such that Q HA such that Q convection is equals to Q conduction. That is HA Ts T finite is equals to minus Ka dt by dy, such that our H is equals to, the A cancels out, so we are left with a K minus dt by dy divided by Ts by T finite. Now you can see that H is highly dependent upon the conductivity of the fluid, and inversely so with the temperature difference, right? But it is also proportional to the temperature difference or gradient dt by dy. So now, as we have seen, knowing Ts and T finite is not a major problem. And knowing the surface area is not a major problem. The major problem or the main work is to determine our H. And to do that, we'll need a lot of knowledge and relevant tools to determine that H. So now, H, as we've seen, is highly dependent upon the conductivity and inversely proportional to the boundary layer thickness delta. And this delta is dependent, so delta is dependent on the nature of the fluid, that is viscosity. It will also be dependent upon the velocity of flow of the fluid. It will also be dependent upon specific heat capacity of the fluid. So in general, we can say that our H is equals to a function of the density d, which is the characteristic length, that is dependent upon the geometry of the surface. It's also dependent upon the velocity of flow, the kinematic viscosity mu, the specific heat capacity C, and we've seen it is also dependent upon K. Now, in our analysis, we will apply dimensional analysis to get hold of the necessary tools to determine H. And because I remember we did fluid mechanics together, I believe you can still remember what we did in a dimensional analysis. But let us have a recap on dimensional analysis. So supposing we have a physical system, and these physical systems has a number of variables. Supposing one of the variables is x1 and it is a function of x2, x3, x4, xm. So it means that we have m number of dependent and independent variables. So that is dependent, and these are independent variables. And supposing all these variables are constituted from n number of primary or basic variables. So when we analyze for dimensional homogeneity, we found that this gives us a result whereby we get groups. So the results give us groups of dimensionless numbers that we call pi terms. So if we have m a number of variables and n basic units or variables, we saw that we expect m minus n number of pi terms. So supposing we have x1, which is a function of x2, x3, all the way to xm, and we have n number of basic variables or basic dimensions, that is dimensions that are not dependent on any other, then we expect m minus n number of pi terms such that you have one of the pi terms dependent upon pi term 2, pi term 3, all the way to pi term m minus n. And all these pi terms are made up of the same number of variables. So all the pi terms have the same number of variables, and this number of variables is n plus 1. Now, out of this number of variables, n plus 1, n number of variables are repeating variables, i.e. they will appear in all the pi terms. So in fluid mechanics, we dealt only with these basic dimensions: mass for m for mass, L for length, and T for time. Well, we can just use capital T believe it will not confuse us, T for time. So in fluid mechanics, we are not so much interested in the variation of temperature. But in thermodynamics, you find that temperature is a major factor. And as you've seen, we've been dealing with temperature differences. And in most cases, we have denoted our temperature difference by theta. So it means that in our analysis, we will be having 1, 2, 3, and 4 basic dimensions. So 4 basic dimensions. So looking at our case whereby we have h is equals to a function of rho d v mu or eta, if you like, c and k, you find that we have 1, 2, 3, 4, 5, 6, 7. We have a 7 number of variables, and as we've seen, the number of basic dimensions is 4. So we expect 7 minus 4, that is 3 pi terms, and these pi terms will be made up of 4 plus 1 number of variables, i.e. 5, and 4, that is n, will be repeating. Variables. Before we move on, let us analyze all the variables dimensionally. So we have h, which is defined as or has SI units of a watt per meter squared, Kelvin. So we have watt dimensionally, that is the rate of doing work, is force, and force is a mass times the acceleration, all right, times a length to give us work, divided by time to give us the rate of doing work, and we're dividing that by temperature difference, which we are denoting by theta. So dimensionally h has m Okay, and this is per unit uh, area. So the L's cancels out, so we are left with m t negative 3 and theta raised to the power of negative 1. So we can repeat the same thing for density, and you'll get, for density denoted by a rho, the dimensions are ml negative 3. Supposing the fluid is flowing over or inside some tube of diameter d. So the dimension for d is L. Velocity is distance per unit time, Lt negative 1. Fluid viscosity by m L negative 1 T negative 1. Specific heat by L squared T negative 2 theta negative 1, and thermal conductivity by m Lt negative 3 theta negative 1. So let us go back to our is a function of h rho d v mu c and k. So what this means is that, let us know the choice of the repeating variables depends on the experience of the analyzer, and I believe you can remember how we went about determining our repeating variables. But supposing our repeating variables are h rho d and v, this implies that our pi term 1 will have h raised to the power of a. So h to the power of a, rho to the power of b, d to the power of c, and v to the power of d times one of the non-repeating variables, let's say mu. Pi term 2 will be composed of the same number of repeating variables, let's say a1 raised to the power of a1, rho raised to the power of b1, d raised to the power of c1, v raised to the power of d1, and multiplied by a non-repeating variable, let's say c, and the last pi term 3 will be made up of the repeating variables times the remaining non-repeating variables k. So let us analyze pi term 1. So for pi term 1, we have m raised to the power of 0, l raised to the power of 0, t raised to the power of 0, and theta raised to the power of 0, because it is a dimensionless number, is equals to mt minus 3 theta minus 1 all over that to the power of a1 or to the power of a times ml negative 3 to the power of b times l to the power of c lt to the power of negative 1 to the power of d, and lastly m l negative 1 at t negative 1. So analyzing for dimensional homogeneity, for m, find that 0 there is equals to a1 or is equals to a plus a b plus 1. So for L, we have 0 is equals to minus 3b plus d plus c plus d minus 1. For t, we have 0 is equals to minus 3a minus d minus 1. And lastly, for theta, we have 0 is equals to minus a, so it means that a is equals to 0. So solving all the simultaneous equations, you'll get a is equals to 0, b is equals to negative 1, c is equals to negative 1, and d is equals to negative 1, such that we have now our pi term 1 is equals to mu divided by rho divided by d divided by v. For pi term 2, we have m0, l0, t0, and theta 0 is equals to mt negative 3 theta negative 1 A1 ML negative 3 B2 B1 L C1 LT negative 1 D1 times L squared T negative 2 theta negative 1, that is for C, and again repeating the same procedure, that is for homogeneity. For M, 0 is equals to A1 plus B1. For L, 0 is equals to minus 3B2 plus C2 plus D2 plus 2. This is C1, B1 and D1. All right. And for T, we'll have zero is equals to minus 3A1 minus D1 minus 2. And lastly, for theta, 0 is equals to minus A2 minus 1 . And that implies that solving the simultaneous equations, you'll get A1 is equals to negative 1, B1 is equals to 1, C1 is equals to 0, D1 is equals to 1, such that our pi term 2 is equals to rho V C divided by H. But the dimensions of H, all right, which is watt per meter squared Kelvin, is equivalent to that of the conductivity divided by D. We can substitute for H in this equation by K over D, such that our pi term 2 is equals to C rho V. Instead of H, we have K over D. So let's have a look at pi term 3. Again, we'll have M naught, L naught, T naught, theta naught is equals to MT negative 3 theta negative 1, A2, ML negative 3, B2, L C2, LT negative 2, not negative 2 but negative 1, D2, and lastly multiplied by M L T negative 3, theta negative 1, and checking for dimensional homogeneity, you'll get for M, 0 is equals to A2 minus 3B3, 3B2 plus 1, and for L, 0 is equals to minus 3B2 plus C2 plus D2 plus 1. For T, 0 is equals to minus 3A3 minus S2 minus D2 minus 3 and we have for theta 0 is equals to minus A3 minus 1. Solving the simultaneous equations, you get, this is A2, you will get A2 is equals to negative 1, B3 is equals to 0, C3 is equals to, C2 is equals to negative 1, and D2 is equals to 0, such that your pi term 3 now is equals to K over HD. So it means that our K over HD, that is the pi term 3. So now we've seen that our pi term 1 is equals to mu over rho dV. But one thing that you should note is that if that is a dimensionless number, then even its a reciprocal, rho dV over mu, is also a dimensionless number. So that and that are equivalent. Okay? And also, we found out that pi term 2 is equals to C rho V D over K, and pi term 3 is equals to K over H A D. Now, again, this is also equivalent to dimensionally HD divided by K. Now, if you look at all those pi terms, you find that pi term 3 carries with it H, and in our analysis, we are more after the heat transfer, convective heat transfer coefficient H. So I would like HD over K to be our subject. So HD is equals to a function of, okay, it is a function of pi term 2 and pi term 1. So it is, and pi term 2, which is C rho V A D over K. Now, if you look at this pi term C, let us use a different color. C rho V D over K. Supposing you multiply the numerator by mu and the denominator by mu. So this will give C times rho Vd times mu over mu AK. That is still a pi term. But I know that mu C over K is a dimensionless number that is called the Prandtl number. So this is made up of mu C over K times rho V D over mu. So we can say that our HD over K is equals to a function of rho dV over mu and mu C over K times rho V D over mu. And as you can see, we have a repetition here of rho dV over mu, rho Vd over mu. So we can just state as that our pi term 3 HD over K is equals to a function of rho dV over mu and mu C over K. And we have our three-dimensionless number, and this first dimensionless number is called the Nusselt. The Nusselt number. This is the famous Reynolds number, and that number is called the Prandtl number. So we can say that the Nusselt number is a function of the Reynolds number and the Prandtl number. Or the Nusselt number is equals to a constant of proportionality which we can denote by a lambda Re raised to the power of some number A and Prandtl number raised to the power of some number P. So that is the resulting relationship between the dimensionless numbers. Now, the analysis that we've made here is for forced convective heat transfer for turbulent flow. And one thing that should be noted is that when it comes to heat transfer, by convention, would desire the fluid to be as turbulent, the flow to be as turbulent as possible, because it enhances the mixing of the fluid and hence the transfer of heat. But of course, there will be some limitations as far as the extent to which we can cause our fluid to flow turbulently. So now let us have a look at dimensional analysis for natural or free convective heat transfer. And as we have seen before, H is a function of V or rho K mu C, and the characteristic length, you can either use D or L. Okay, so supposing delta T is the temperature difference between the fluid and the solid. All right, now in our analysis for forced convective heat transfer, we used V as it was. But at this time round, V is no longer an independent variable, so V is no longer an independent variable. So our V this time is dependent upon some other variables, and these variables are: one, that temperature T, delta T; two, a beta, and beta is called the coefficient of volume expansion of the fluid, and three, G, which is the acceleration due to gravity. So our V now is dependent upon G, beta, and delta t. That is what we shall put into our relationship equation above. So we have h is equals to a function of rho, let us use L this time round, mu C K beta G and a delta T, this lumped together to make one variable. So again we have how many variables? We still are having 1, 2, 3, 4, 5, 6 and 7, because this is lumped together to come up with one variable. So we have now 7 and n still remains 4. Therefore, we expect m minus n, which is 7 minus 4, which is equals to 3 pi terms. Okay? Such that pi term 1 is equals to a function of pi term 2 and pi term 3. So, supposing we took rho L, mu and k as the repeating variables. So pi term 1 will be given by a rho to the power of a, L to the power of b, mu to the power of c, k to the power of d, and the first a dimensionless or a non-repeating variable, which is, let's say, h. Pi term 2 is equals to rho a1 L b1 mu c1 k d1, and the next non-repeating variable c, and then lastly pi term 3 rho a2 L b2 mu c2 k d2 times the last non-repeating variable bg delta t. So dimensionally we have for you analyze that, you'll get it to be equivalent to LT negative 2, and we have all the rest or other dimensions, or the rest of or dimensions for the rest of the variables. So now let's have a look at pi term 1. We have m0, l0, t0, theta 0 is equals to ml negative 3a, lb ml negative 1, t negative 1 c, ml t negative 3 theta negative 1 d times ml negative 3 theta negative 1, that is our h. So for homogeneity 0, that is for m, 0 is equals to a plus c plus d plus 1. For L, we have 0 is equals to minus 3a plus b minus c plus d. For T, we have 0 is equals to minus c minus 3d minus 3. And lastly, for theta, we have 0 is equals to minus d minus 1, which implies that d is equals to minus 1. Now, if you solve the simultaneous equations, you get a1 is equals to 0, b1 is equals to 1, c1 is equals to 0, and d1 is equals to negative 1, such that our pi term 1 is equals to HL over K. So let us have a look at pi term 2. So we have again M0, L0, T0, theta 0 is equals to ML negative 3 A1 L B1 ML negative 1 T negative 1 C1 ML T negative 3 theta negative 1 D1 and L squared T negative 2 theta negative 1 4 our C. Again, for homogeneity, we have for M 0 is equals to A2 A1 plus C1 plus D1. For L, 0 is equals to minus 3A1 plus B1 minus C1 plus D1 plus 2. For T, 0 is equals to minus C2 C1 minus 3D1 minus 2, and lastly for theta 0 is equals to minus D1 minus 1, which implies that our D1 is equals to negative 1. And solving the simultaneous equations for the rest of the dimensions, you get A1 is equals to 0, B1 is equals to 0, C1 is equals to 1, and of course we found that D1 is equals to negative 1. So pi term 2 is equals to mu times C over K. Now let's have a look at the last pi term, that is pi term 3. So for pi term 3, we have m naught, l naught, t naught, theta naught is equals to ml negative 3, ml negative 3 b2, ml negative 1 t negative 1 c2, ml t negative 3 theta negative 1 d3, and lastly we multiply that by the dimensions for delta t g beta, which is that. So for homogeneity, we have for m, 0 is equals to a3 plus c3 plus d3, 0 for that is for L is equals to minus 3a3 plus this is 2 plus b2 minus c2 plus d2 plus 1. For t, 0 is equals to minus c2 minus 3d2 minus 2, and for theta, 0 is equals to minus d3, which implies that d3 d2 is equals to 0. Solving the simultaneous equations, you get a3 a2 is equals to 2, b2 is equals to 3, c2 is equals to negative 2, and of course we found that d2 is equals to 0. So our pi term 3 is beta g delta t times rho squared times L cubed divided by mu squared, which is equivalent to beta g delta t times L cubed over nu squared because we have the dynamic viscosity mu divided by the density rho is equals to the kinematic viscosity. So mu squared divided by rho squared is equals to the kinematic viscosity squared. All right, so that is our third pi term. So we can say now that our first pi term HL over K is equals to a function of the second pi term, which is, as we've seen, mu C over K, and the third pi term, which is beta G delta T L cubed divided by nu squared. And this dimensionless number, as we've seen, is called the Nusselt number. This is called the Prandtl number, and this is called the Grashof number. So we've seen that for a free convective turbulent flow, convective heat transfer, the Nusselt number is a function of the Prandtl number and the Grashof number, such that the Nusselt number is equals to a constant of proportionality. Let us put C PR to the power of some constant. Let's use N, and Grashof number to the power of M. So that is the probable relationship using the dimensional analysis tool for a forced convective heat transfer. Now let us do some examples. An airfoil with a characteristic length of 0.15 meters and a surface temperature of 325 degrees is placed in an airflow at 37 degrees with a free stream velocity of 100 meters per second. And it is observed that the rate of heat transfer from the airfoil is 1600 watts. So if we have a second airfoil with a characteristic length of 0.3 meters and the surface temperature of 425 degrees and is placed in the airflow at 37 degrees C, but this time with a velocity of 50 meters per second. You're told to determine the rate of heat transfer from the second airfoil. And you're told that the surface area of the airfoil may be assumed to be directly proportional to its characteristic length. So I have the two airfoils, that one and that one. And we have these two streams of air flowing over the airfoil. So let us have a look at the solution. We have seen that for a forced convective heat transfer, the Nusselt number is a function of the Reynolds number and the Prandtl number. And we know that the Nusselt number is equals to h times the characteristic length L or D over K, and the Prandtl number is given by C mu divided by K. Whereas the Reynolds number, we know it is rho V times L divided by mu. So for the airfoil 1, the Reynolds number is equals to remember that if you divide the mu by rho, you get eta. You get a nu when u is the kinematic viscosity. So this is the same as a V1 L1 divided by the kinematic viscosity 1, which is equals to 100 times 0.15 divided by nu. Okay, because nu is a fluid's property and we are told that they are not changing. This is equals to 15 over nu meter squared per second. The Reynolds, it cannot be because it is a dimensionless number, doesn't carry. So the Reynolds number 2 is V2 L2 over nu2, but we've seen that the nu is not changing, so this is this will be 50 times L, which is 0.3 divided by nu, which again is 15 over nu. So since the properties of the fluids are not changing, it follows that the Nusselt number 1 is equals to the Nusselt number for airfoil 2, such that H1 L1 over K is equals to H2 L2 over K. This implies that H2 is equals to L1 over L2 times H1. But we know that Q is equals to H1 times A1 times Ts, let's say 1 minus the environment is not changing, so we have T finite, such that H1 is equals to Q divided by A1 Ts 1 minus T finite. So this implies that H2 is equals to our H1Q over A1 TS1 minus T finite times L1 over L2. So what does this mean? It means that now, since we know that Q2, which is equals to Q2 is equals to H2 times area 2 times TS2 minus T finite. And we've seen that H2 is equals to Q1 over A1 TS1 minus T finite, and we are multiplying that by A2. Okay, and there was some L1 over L2. Is it yeah, A2 times TS2 minus T finite. But we are told that the area of the airfoil is proportional to its length. So it follows that A is equals to a constant of proportionality times L. Let us use P for the constant of proportionality, or we can use lambda for the constant of proportionality, such that area 1 is equals to lambda times L1 and area 2 is equals to lambda times L2, right? So we have our Q2 is equals to Q1 times area 1, okay, times L1 times L2, and L2 we've seen is equals to A2 is equals to L2 lambda, and we're dividing that by area 1, and area 1 is equals to L1 lambda, and we're multiplying that by L2, and down here we have TS1 minus T finite. Up here we have TS2 minus T finite. So as you can see, L1 times lambda times L2, L1 times L2 lambda cancels out. So we're left with Q2 is equals to TS2 minus T finite over TS1 minus T finite multiplied by Q1, and that is TS2 425 minus 37 over 320 minus 37 times 1600, and that will give us 2156 watts.